Back to another lesson in pre-calculus. Today we're going to be focusing on rational functions. Now we just finished up polynomial functions, and today we're going to be looking at rational functions. And rational functions, rational, the word ratio is in it, is a ratio of two polynomials. So if you take a polynomial and you divide it by another polynomial, you'll get a rational function, a ratio, a fraction. Okay, for example, the function, x minus 2 over x squared plus 3. That is a rational function. It's a polynomial divided by a polynomial. And what you'll notice in rational functions that's very different from just looking at polynomials is the domain is often restricted. That means that there are values that we're not actually able to input into the function for a variety of reasons. So again, sorry, it's early in the morning when I'm recording this. The domain is all of the possible inputs. When I say inputs, I'm thinking x values into the function. So everything that we are able to input into the function. When we write domain, we're going to write it in interval notation. And what you notice in polynomials, so in polynomials, domain, the domain was always negative infinity to positive infinity. And that's because there was no fractions or radicals in a polynomial. But here, in a rational function, we do have fractions. So therefore, we're going to have values that we're not able to input. And that's because when we have a fraction, the one number we're not allowed to divide by is 0. So anytime we get a 0 in our denominator, we're going to have issues. So let's look at some examples. It says find the domain of the rational functions. So I'm going to start with number 1. And when I have a fraction, the only thing I can't do is I can't have a number over 0. A number divided by 0 is undefined. A 0 divided by a number is just 0. That's cool. But this is not cool. Okay? So I got to figure out where my denominator is 0. Because whenever my denominator is 0, I need to eliminate it from my domain. So I got to figure out when this denominator equals 0. Now we just did this, we just factor it. So what multiplies to negative 30 and adds to negative 13? That is negative 15 and 2. So this is just my denominator. Okay, I don't care about a numerator because I only care about when my denominator is 0. I set each of these equal to 0, and I get x equals 15 and x equals negative 2. Now, even though we got x equals, we're talking about domain, we're really saying, hey, x cannot be these values. Because when I plug these values into my function, I get 0 in my denominator. So I need to somehow write the domain as everything except for negative 15 and negative 2. So we're still going to use interval notation. So we're going to go negative infinity, because that's the smallest value we can input, all the way to negative 2. But negative 2, there's a break. I'm not allowed to input negative 2, so I use a parenthesis to show that I am excluding this value. Then we put a little union, and then we start from negative 2 all the way to 15. Can't input 15, so I use a parenthesis, and then we go from 15 to infinity. So this is interval notation, where we are just excluding the values negative 2 and 15. If I was to draw this on a number line, here is, let's go, this is 0, this is negative 2, and this is 15. I would put an open circle at negative 2 and 15 because I can't input those values, but I can input everything else. So I would do that, and then this, and then that. So you'll see that this corresponds to this interval, this corresponds to this interval, and then this corresponds to that interval. Okay, let's do one more. Again, I'm looking at when my denominator is 0 because I have a rational function and I can't divide by 0. So can I factor this? I certainly can. It would be x plus 2, x minus 1. So I get x cannot be negative 2 or 1. Again, my domain, I can input negative infinity all the way to the smallest value, which is negative 2. I'm going to exclude negative 2, so use a parenthesis, union, and then I have negative 2 to 1, and then I have 1 to infinity. And these are the values I can input, right? We started off by solving what we cannot input, but ultimately the domain is what I am allowed to input. I'm allowed to input anything except for negative 2 and 1. Okay. All right. Now, as you saw in your investigation on Thursday or Friday, depending on when you're watching this, you saw that these functions have these crazy things called asymptotes. Now, you probably looked at asymptotes in the past, but we're going to dive right into their details. So an asymptote is a line. And first of all, let's start with that. It is a line, meaning that every time you write an asymptote, it needs to be an equation. Because an asymptote is a line. It's a line that your function approaches. Okay? It's possible for a function to actually cross over the asymptote depending on what kind of asymptote you have. Okay? So just so you're all clear, it's 5:58. That's why I'm yawning. AM. A line that your function approaches. So there are a couple types of asymptotes. The first one we're going to look at is a vertical asymptote. Vertical. And a vertical asymptote occurs at the values where the denominator is equal to 0. That's funny. We just looked at domain and we set our denominator equal to 0. Well, that's because what we were finding is we were finding the actual vertical asymptotes. So that's why if you have found the domain, you have found the asymptotes. Or, I guess, vertical asymptotes. Sorry. I'm going to call them VA. Is that okay? Vertical asymptotes. Because asymptotes are a line, they need to be an equation. So the equation for the vertical asymptote is x equals a being a number. So x equals 4, x equals negative 1, x equals 7, okay, where a is the 0 of the polynomial in the denominator. Okay. There can certainly be more than one vertical asymptote, and this is a type of asymptote that your function will never ever cross. So when you have a vertical asymptote, if you draw me a vertical asymptote, like I'll draw one here. If this is your image, you draw a vertical asymptote, and then you draw me a function that looks like this, I'm going to tell you you're wrong. There's no way a function can go through a vertical asymptote. Okay, so let's find some vertical asymptotes. Here I'm looking for my denominator is equal to 0. So can I set this equal to 0, and can I factor it? I certainly can. X plus 4, x minus 2. So I have two vertical asymptotes. My vertical asymptotes are at x equals negative 4 and x equals 2. Over here, I have this equal to 0. I can factor an x out, and I'm left with x squared minus 5. So I'm actually left with 3 vertical asymptotes. I have x equals 0, and then I have x equals the square root of 5, and then I have x equals negative square root of 5. Because don't forget, when I do x squared minus 5 is equal to 0, I get x squared equals 5. I get x equals plus or minus 5. Every time you take a square root, you need to do plus or minus. So I have 3 vertical asymptotes in this function here. All right. The next kind of asymptote is a horizontal asymptote. Okay? Horizontal. And a horizontal has 3 different rules. Rule number 1, when the degree of the numerator of the rational function, so we're talking about the numerator, which means the top, right? Top. And degree means power, the highest power, of a rational function is blank, then the degree of the denominator. The x-axis, or y equals 0, is a horizontal asymptote. So when the degree of the numerator is smaller than the degree of the denominator. So for example, x minus 2 over x squared plus 7. The degree of my numerator is 1. The degree of my denominator is 2. So the degree on top is smaller than the bottom, and therefore the horizontal asymptote here is y equals 0. It's just the x-axis. Rule number 2, when the degree of the numerator of the rational function is bigger than the denominator, there is no horizontal asymptote. For example, x squared plus 7 over x minus 2. Now my degree on top is 2, my degree on top is 1. There is no horizontal asymptote here. And rule number 3, when the numerator and denominator of a rational function have the same degree, the line y equals a over b is the horizontal asymptote, where a and b are constants. Okay, so for example, if I have the function 3x squared plus 4 over 2x squared minus 7, the degree on top and the bottom are the same. So therefore, I'm going to divide the leading coefficients of my highest degree. So I get y equals 3 over 2. That is my horizontal asymptote for that example. Okay, the equation for a horizontal asymptote is going to be y equals a. Okay, where it's got to be an equation, right? Y equals a. Horizontal asymptotes, they can sometimes cross. The function can sometimes cross it. What happens sometimes is that you have a horizontal asymptote. Like, let's draw one over here. So here we go. I'll draw a horizontal asymptote here. Sometimes you'll have a function that does this. Alright? I'll put it in blue. It'll start here. It'll cross the horizontal asymptote, and then it will approach it from this side. Okay? That's okay. There are times when a horizontal asymptote can be crossed, and there are times when it can't be crossed. And we'll look into that in more examples. So don't be freaked out if you see a graph that crosses a horizontal asymptote. It's okay. So again, the graph of the irrational function will never cross a vertical asymptote, and it can sometimes cross the horizontal asymptote, but not always, obviously. So the polynomial function may or may not cross the horizontal asymptote. Like the example I just showed you, where it could cross and then come back. let's look at some examples of horizontal asymptotes. Find all the horizontal asymptotes. So in where'd it go? In this one, I'm looking at the degree, and according to my rules, if the degrees are the same, which they are, then I divide the leading coefficients. So the degree on top is 4, the degree on the bottom is 4, so I end up with y equals negative 7 over 11. On this one, I end up looking and I see my degree on top is a 1, and my degree on bottom is 3. And since the degree on top is smaller than the one on the bottom, I know that rule number 1 says it's going to be y equals 0. Okay. You are 99% of the time, 99% of the time going to have only one horizontal asymptote. We won't really look at ones that have more than one horizontal asymptote, but you will in calculus. So I won't say never, but there are times when you do have 2 horizontal asymptotes. And the third kind of asymptote, okay, it's called, you might hear it as an oblique or a slant asymptote. And these are slanted lines of discontinuity, and they only occur when the degree of the numerator is exactly 1 bigger than denominator. For example, if I have x cubed plus 7 over x squared minus 1, the degree of my numerator is exactly 1 bigger than the degree of my denominator. And therefore, I would have a slant or oblique asymptote. Okay? And because it's a slant or oblique, it becomes in the form y equals mx plus b, which is the equation of a line that you have known and loved since 7th grade. Okay. A horizontal asymptote and oblique asymptote cannot happen at the same time. Now, I'm not going to answer that. Right? The question is why? Why can't it happen? Well, I'm going to ask you that. So I want you to think about that. Why can an oblique asymptote and a horizontal asymptote not happen at the same time? Okay? And just like horizontal asymptotes, slant asymptotes may or may not be crossed. So it's possible to cross a slant asymptote. The only one you can't cross is a vertical asymptote. Okay? So let's find some asymptotes. Let's do one example together. So it says find all of the asymptotes here. All of them. The easiest ones are vertical. So let's start with vertical. Oh, let's go. VA. Vertical asymptote. That's when I set my denominator equal to 0. And I end up with just x equals 2. Nice. Check. Horizontal asymptotes. Well, according to my rule, the degree of my numerator is bigger than the degree of my denominator. So there are no horizontal asymptotes. And then slant asymptotes, which I'll call SA. Okay? The degree of my numerator is exactly 1 bigger than the degree of my denominator. So I need to find the slant asymptotes. In order to find them, I need to do polynomial long division. Here we go. 2x squared minus 3x minus 1. When I'm doing polynomial long division, I look at this term and I say, okay, what do I multiply this term by to get 2x squared? And the answer is 2x. So when I write 2x, I'm going to keep my degrees the same. So I'm going to put a 2x here because this is where all my degree 1 values are. So then I do 2x times x to get 2x squared, and 2x times -2 to get -4x. Then I'm going to take these values and I'm going to subtract them from the previous values. So 2x squared minus 2x squared, they go away and give me 0. That's what we want. -3x minus -4x gives me positive x, and I'm going to bring down the -1. Now, what do I multiply x by to get x? The answer is 1. So I'm going to put a +1 up here. And then I do 1 times x, gives me x. 1 times -2 gives me -2. Of course, I'm going to subtract these values from here. X minus x gives me 0. -1 minus -2 gives me a positive 1. Now, can I multiply x by something to get 1? The answer is no, you cannot. So this is our remainder. And when we're doing slant asymptotes, this is not important. All we care about is this guy right here. Okay? This is our slant asymptote. It is the function y equals 2x plus 1. And these are my two asymptotes. Before I let you go, I'm going to graph this so you can see exactly what I'm talking about. So let's pull up Desmos. So it's 2x squared minus 3x minus 1 divided by x minus 2. So here's the function that you get. You'll see if you zoom out, it looks really funky, right? According to us, we should have a vertical asymptote at x equals 2. Haha, there it is. In fact, I can make this thing dotted if I wanted to. That's a vertical asymptote. And then I can also graph my slant asymptote, which is y equals 2x plus 1. And I can make this dotted as well. And there you will see that my asymptotes are really dictating how this function behaves. Okay. Great. I hope you all learned something about asymptotes, and I'll see you next time on part 2 of rational functions.